And we'll move on to our final talk from Aravindan Benjamin, who is also from the University of Oldenburg. And he's talking about mixing preferences of hearing impaired listeners. So if you'd like to share your slides, and then we can kick off.
Yeah.
Okay.
Hello there. I would like to first run it because I have some audio samples, and I would like to know if you can hear the audio. Was that audible?
I don't think so. It's very quiet. When you share your screen, there is a little tick box at the beginning that says include computer sound. Can you see that?
Oh yeah. Yeah. So let me try that again.
Sorry, everybody.
Yes, this one. I don't get that option, unfortunately. Yeah, thank you very much, everybody. Hello there. I'm Aravindan Benjamin from the Music Perception and Processing Lab at the University of Oldenburg, headed by Kai Siedenberg. It gives me great honor to present our study titled Mixing Preferences of Hearing Impaired Listeners today. So, multi-track mixing is a rather ubiquitous, albeit arduous practice, which can see benefit in being automated. Existing mixing paradigms have been tested mostly on trained, normal hearing participants. To assist in this field, we aim at assessing level and spectrum-based mixing effect preferences in multi-track mixes among hearing impaired listeners. Furthermore, we aim at assessing the effect of bilateral hearing aid use in such preferences. Similar studies have been performed mostly on cochlear implant users. Bynes et al. And Pons et al. Showed that cochlear implant users preferred higher levels of lead vocals in the multi-track mixes. Nagatil et al. Showed that spectral complexity reduction in classical chamber music saw an improvement in preference ratings among cochlear implant users. As only normal hearing and cochlear implant users have been tested so far, here we target hearing impaired listeners without cochlear implants. Throughout our study, we used the open source Medley and Cambridge MT databases. 2 independent studies were conducted. In the first study was to assess mixing preferences among the participants. This was completed using 2 independent experiments. In experiment 1, normal hearing participants, aided or bilateral hearing aid users, and unaided or non-users were considered. In the second, more controlled experiment, only aided participants were considered. I would like to mention that from here on, by aided or hearing aids, I always refer to bilateral hearing aid use. Study 2, which is a work in progress, the musical scene analysis ability in detecting target tracks within a mix was assessed. Here, only normal hearing and unaided hearing impaired participants took part. As for the mixing effects, there were 3 such effects considered. The first effect was a level-based effect called lead to accompaniment ratio, or LAR, measured in decibels, which is merely the difference between the broadband levels of the lead vocals and the accompaniment in a given multi-track mix. This was altered by changing just the levels of the lead vocals alone, leaving that of the accompaniment untouched. The second was a spectrum-based effect referred to as a spectral balance implemented by Siedenberg et al. This effect is measured in decibels per octave. The spectral balance is applied by changing the slope of the pass band applied on the final mixdown rather than on the individual tracks. This effectively changes the weighting applied at frequency above and below 1 kHz as shown. Lastly, the EQ transform measured as a percentage of the original EQing is considered. This spectrum-based effect aims at reducing or exaggerating the coloration applied by the mixing engineer during EQing. The EQ transform is achieved by linearly extrapolating between a reference spectrum specifying 0% EQ transformed and the original or factory spectrum at 100%. The reference spectrum is the ensemble average of the most commonly occurring instruments in both databases. As illustrated, the EQ transform is applied on each track separately. In the next slide, I'll provide a summary of what happens here. Here, I wish to outline how the EQ transform was implemented. Firstly, in the analysis block, we take a full-length FFT to evaluate the power spectrum of the track. Then, we linearly extrapolate between the original or factory power spectrum and the reference power spectrum to estimate the transformed spectrum. As this transformed spectrum is noisy and may introduce time domain smearing, it is subjected to further processing. The envelope difference between the factory and the transformed spectrum are then evaluated. This envelope difference is then smoothed using a Savitsky-Golay filter to acquire a smooth envelope. And then we use thresholding to acquire significant bands of the input's audio where the power levels do not fall short of 90 dB below the global maximum. Then the smooth envelope is then used to color the significant bands of the input signal, which we acquired earlier, to acquire the final transform mix. In the penultimate step, an inverse transform, Fourier transform is performed to acquire the corresponding time domain representation. Lastly, it is then normalized to have the same broadband energy as the factory input to complete the EQ transformation of that track. I would like to show you some audio examples, unfortunately if you can hear them. So this is actually from the song Hold On You by James May from the medley database. So firstly, I would like to show the factory, which is on the unaltered EQ transform. Then 0%.
I don't think we're hearing any audio there.
All right, yes, I'll just skip to the next slide. Yeah, so to quantify the implications of the EQ transform, we evaluated the Gini index as a measure of spectral sparsity. Hurley and Reichardt demonstrated that the Gini index was originally used in economics to measure wealth inequality, also served as a robust measure of time frequency sparsity and mathematical source separability. For this, we used a constant Q transform-based method where the Gini coefficient of the median spectrogram at third octave bands is evaluated. On the right, we see that with increasing EQ transform, a monotonical increase in spectral sparsity by way of an elevated Gini coefficient is shown. Below, you can also see that the EQ transform also brings about spectral sparsity in the final mixdown. Here, I would like to talk about the setup of the listening test and procedure. For the first setup, a stereo speaker setup illustrated was used. The overall playback level was adjusted at 80 dBA at the participant position. The participant chooses the audio effect preference with a virtual dial. The effects are realized real-time upon rotating the dial. Throughout this study, only 8 seconds of the multi-track excerpts were used and looped indefinitely. In experiment 1, lead to accompaniment ratio, spectral balance, and EQ transform blocks are presented via 10 trials of 10 multi-track excerpts. The order of the presentation was randomized. Here, aided participants were requested to retain their hearing aids during the entire course of the experiment. In experiment 2, albeit identical to experiment 1, was more controlled. As mentioned earlier, here only aided participants were considered. Six sets of 10 multi-track excerpts were used. These were assigned to corresponding blocks randomly. The blocks themselves were repeated in 2 phases. In one phase, the participants were requested to use their hearing aids, and in the other, they were asked to remove them. Here, I would like to talk about the participants themselves. So in experiment 1, 25 normal hearing participants took part, 10 aided and 10 unaided participants and hearing impaired participants took part. The hearing aid users were marginally older and suffered more hearing loss than their unaided peers as shown. As per the classification by Clark et al. In their 1981 publication, all unaided hearing impaired participants had mild hearing impairment. 50% of the aided participants, however, had moderate to severe hearing impairment. In experiment two, 18 aided participants took part. Only 4 among them had mild hearing impairment. The participants' ages correlated positively with mean hearing loss level in both experiments. So I'd like to discuss the results that we found in experiment 1. It was shown that aided participants preferred significantly elevated lead vocals than that of their normal hearing peers. There were significant individual differences in lead to accompaniment level preferences among the unaided participants compared to those of the normal hearing ones. Unaided participants preferred greater weighting at frequencies above 1 kHz. Normal hearing participants preferred significant undermixing or that below 100% in the EQ transform preferences. Comparing the matched sample in experiment 2 with and without hearing aids disuse saw a 5 dB higher preference in lead to accompaniment level ratios in the mixes. This was similarly so with a 2 dB increase in weightings at frequencies above 1 kHz with hearing aids disuse. Elevated weighting preferences from factory settings were observed with hearing aids disuse at frequencies greater than 1 kHz. This was conversely so with hearing aids use with elevated weighting preference at frequencies below 1 kHz. Significant overmixing above factory settings were observed by way of elevated EQ transform preferences with hearing aids disuse. To ascertain the effect of mean hearing loss, we consolidated unaided data with from both experiments and normal data from experiment 1, normal hearing data from experiment 1. A positive correlation between mean hearing loss and lead to accompaniment ratio and mean hearing loss in EQ transform preferences was shown. However, this did not, the correlation between spectral balance and mean hearing loss was very poor. So in the independent study, which I mentioned as a work in progress, was conducted to assess musical scene ability as a function of hearing impairment and spectral sparsity of the mix. The setup was identical to previous studies and the procedure identical to that of Robin Hacke's experiments. Target was played and the mix followed in the MSA phase. Both target and the mix were 2 seconds long. The targets was one of 5 categories, which were lead vocals, bass, drums, guitar, and piano. The mix sparsity was altered using the EQ transform. 30 normal hearing and 24 hearing impaired, of whom 3 were not of mild hearing impairment. As shown here, the hearing impaired listeners had approximately 40 dB greater hearing loss compared to those of normal hearing. Hearing aid users did did the experiment unaided, so all the hearing aid users were asked to remove their hearing aids. So we used a generalized linear mixed effects model to analyze the dichotomous data. That was a correct or wrong answer to what they were, which we accrued over the course of the experiment. Hearing loss indeed depreciated performance from what we discovered. Mixed sparsity improved performance with hearing loss and target class notwithstanding. With hearing loss notwithstanding, mixed sparsity improves performance with for trials with lead vocal targets. However, this depreciated performance for guitar and piano targets. However, the trials with lead vocal targets increasing hearing loss saw a significant drop in performance for sparser mixes. For guitar targets, the performance drops brought on by hearing loss were mitigated by increased mix sparsity. So in conclusion, aided participants preferred elevated lead vocal levels in the mixes than normal hearing participants. Hearing aid disuse among aided participants saw an increased preference for higher level lead vocal levels, more weightings at high frequencies, and spectrally sparser mixes. Mix sparsity improved performance for lead vocals and depreciated performance for guitar targets regardless of the degree of hearing impairment. However, depreciating performance with hearing loss was worse for sparser mixes when targets were the lead vocals. The depreciating performance brought on by hearing loss was mitigated when the targets were guitar tracks. Our investigation suggests that adjusting mixes can indeed make them more accessible and transparent to hearing impaired listeners. I would like to ask that you refer to the JASA publication if you wish to learn further, get further information about my first study. Thank you very much for your attention. These are my references. Any questions?
Thank you very much for the very interesting talk. Yeah, have we got any questions straight away, or otherwise I've got a very quick one. I'll jump in with my question then while we're waiting. I was just wondering, it sounds like the people who had hearing aids were asked to take them off and put them on again a couple of times. Did any of them report any problems with doing that, or were they happy with that?
I didn't get any feedback regarding that from the from the participants, so there were no comments.
No comments is good news, I suppose. Have we got any questions from anybody here, or would anyone like to write something in the chat? Alenka, you've got your hand up. Go ahead.
Yeah, it's really good to see the combination here of Robin's work on the MSA test being combined. I just wondered if you maybe could reflect on whether sound engineers can use these transforms easily. Do they have access, and what sort of guidelines might be able to be produced?
Oh yes, the sound engineers can use it to a certain degree, but to very high levels of EQ transform, you do get very noticeable distortions. So that appears to be a caveat. So yeah, so it is accessible, and with that being the only shortcoming.
Okay. Any other questions from anybody? No, I think that's it. Okay. Thank you very much for the wonderful talk, and thank you to all our speakers, Kath and Robin as well. It's been a great session.